In this video, we're going to take a look at this technique of substitution and how we use that with definite integrals. So I wanted to start out with a quick reminder of what substitution is with indefinite integrals. So what we're looking at is that we've got a derivative that we found from the chain rule. So that happens when we have a function plugged into another function. So we've seen a lot where you've had, polynomials plugged inside some other function or inside of a signed function. Maybe we've got e to the x. So we've got a function plugged into another function. We took this derivative using the chain rule. So we have the derivative sitting there, and we're going to try to figure out what it was that was the inside function. And once we figure that out, we're going to say, okay, let's let u be that inside function, and then doing a little bit of substitution, changing du to dx. We'll see an example of this, as we go down here. So we'll see this worked out again. But we're hoping to change this into an integral that's a lot simpler that we know how to do with our sort of standard antiderivative rules. So nothing's really going to change with the technique when we do this with definite integrals. We just have to do the fundamental theorem of calculus after we get our integral. What we do have to be cautious about are these limits of integration, because we want everything to be in terms of u, and what might be a little bit nice about this is going to maybe make us have a little less work to do at the end. So I'm going to show kind of two options that you have with this. It doesn't matter which option you choose. It's really up to you. Newton Alta is going to have you practice changing your limits of integration, but it's up to you whether or not you do that. I'll kind of show the way that I do this sometimes when I'm doing, as I would put in my air quotes, a little bit of bad math. So let's take a look at an example here. This is one of the harder ones to see what to do with substitution, but we'll talk more about, like I said in class, of how to identify what it is you should make as u. And one of the options is always taking the more complicated polynomial that you have. So our more complicated one, and kind of what we mean by more complicated, that is that it's got bigger exponents. So we've got an x to the third minus 7, so it's got bigger exponents. We're going to let u be that function that's down on the bottom. So sort of kind of looking at where we are with our substitution part of this, then this is that sort of weird part where we've got things in terms of two types of variables, and this is not great. So what we want to do is take the derivative of u, and we get 3x squared, and we always multiply both sides by dx to get du by itself. And so we get that du is equal to 3x squared dx. And we have 3x squared in our integral right there. So all of that we can replace with du. Let me get a slightly darker color here. So we've got the integral from 3 to 2, so 1 over u du. So this u has to stay on the bottom of that fraction. It's on the bottom of a fraction, it has to stay there. Now, we've got everything in terms of u except for our limits of integration. These are a bit of a problem because these are still in terms of x. And if we're going to be good and proper about this, what we need to do is make them in terms of u, because we want everything in our integral to be in terms of that new variable u. So we can do that really easily. We take u, we plug in 3 into our equation that we made for u. U is x cubed minus 7. So here we get, what, 27 minus 7. So we get 20. U at 2, we get, what, 8 minus 7. So that's 1. So our new limits of integration, 2 turns into a 1, 3 turns into a 20, and we get 1 over u du. So again, the whole point of this was setting this up so this turned into an integral that we know. This is the natural log of the absolute value of u from 1 to 20. And then doing the fundamental theorem of calculus, we don't have to substitute back because we've got our limits of integration. Everything's in terms of u. So we get natural log of 20 minus natural log of 1, and we get natural log of 20. So we can change those limits of integration to get everything in terms of u. I don't always do that. Sometimes I do a little bit of bad math at this point here where we're sitting at this 2 to 3, 1 over u du. And I say, okay, I need to remind myself that those are still in terms of x. So I will often write my limits of integration as x equals 2 and x equals 3 to say those are not u. That's not what my variable is on my limits of integration. But I can still take this integral because I know what it is. It's natural log of the absolute value of u from x is equal to 2, x is equal to 3, and u was x cubed minus 7. And now I don't need to write that x equals anymore because it's from 2 to 3. We're back in terms of our correct variable. So when we use now the fundamental theorem of calculus, we get natural log of 3 cubed minus 7. Hey, wait, we did that up here. Minus natural log of 2 cubed minus 7. Oh, wait, we did that up there. And we still get natural log of 20 minus natural log of 1. So we get natural log of 20. So it really is just a matter of sort of when do you want to plug those limits of integration into that polynomial. Do you want to do it, up here at the beginning, kind of more towards the beginning, or do you want to do it down here? Oops, I'm underlining like crazy. Or do you want to do it down here while you're doing the fundamental theorem of calculus? It's kind of nice to kind of do them off to the side like this, because then your fundamental theorem of calculus over here is pretty basic. But it's completely up to you when you do it. You just have to remember, if you leave them like this, that you should write them as x equals, so that just again to jog your memory that you didn't change those limits of integration. Let's do one more really quick. Sorry if you heard my text message ding there. So here, u is going to be my exponent of e. So u is 2x, its derivative is 2, and we always multiply both sides by that dx. So again, this step right here where I'm multiplying both sides by dx, you can do that, or as you sort of get used to doing substitution, you can go straight to that second step. So what we've got for our integral, and maybe I will be good here and say that these limits of integration are x. So we've got 2 e to the u dx, and then 2 and dx, which we have in our integral, those are both equal to du. I'm sorry, I keep getting text messages. Oh no. So many dings. Sorry about that. So x is equal to 0, x is equal to 1. And we get e to the u du. And by replacing the du with the 2dx, sorry. And so again, you can proceed from here, or if we want to change those limits of integration, we can do u at 1, which gives us a limit of integration of 2, u at 0, which gives us a limit of integration of 0, and so we get 0 to 2, e to the u du. E to the u, it's its own integral, and so we get e squared minus e0, so e squared minus 1. So again, this is exactly the same thing you would get if you didn't change those limits of integration. If we from here went and said, okay, that's e to the u from x is equal to 0, x is equal to 1, u was 2x, then we can go from 0 to 1. We'd still get e to the 2 minus e to the 0. So we get e squared minus 1. So again, like I said, it's really up to you whether you change those limits of integration. You just need to decide which sort of workflow works best for you. And I apologize for the textings during the video.